get more familiar with such things, let me take a third example where I take the same system and displace it by some distance, let us say 0.025 meters, and give it a velocity initially in this direction, negative direction, of let us say 0.05 meters per second. Again, looking at the system, I have xt is equal to c cosine of omega 0 t plus d sine of omega 0 t, where omega 0 is given to be 4 radians per second. I have x at 0 is equal to 0.025, and this is equal to c. So c is already determined. X dot t at t equal to 0 is going to be omega naught d, and this is given to be minus 0.05, and therefore d is equal to minus 0.05 over 4, which is minus 0.0125, and therefore my solution xt is going to be of the form 0.025 cosine of omega 0 t minus 0.0125 sine of omega 0 t, where omega 0 is 4. Let us look at the solution. So xt is equal to 0.025 cosine of omega 0 t minus 0.0125 sine of omega 0 t. If I write it in the form some amplitude cosine of omega 0 t plus phi, you can see that a is going to be a square root of 0.025 plus 0.0125 square, this square, and sine of phi is going to be equal to 0.0125 divided by the amplitude, and cosine of phi is going to be equal to 0.025 divided by the amplitude. Both are greater than 0, and this tells me whatever the value, the phi is between 0 and pi by 2. And therefore, if I plot this function, xt is equal to 0.025 cosine of omega 0 t minus 0.0125 sine of omega 0 t, which we wrote as some amplitude cosine of omega t plus phi, with phi between 0 and pi by 2. It will look like, I am plotting xt versus t. At t equal to 0, the function has already achieved what it would have achieved a little later if the function was pure cosine omega t. So cosine omega t looks like this. This is cosine omega t. The function that I have now is this. It will start somewhere from the back side and go like this. This is cosine omega t plus phi, with phi greater than 0 but less than pi by 2. You can see the velocity is going to be negative because the slope is negative here. It starts from here and becomes maximum at the equilibrium point, then starts going down, goes to 0, becomes maximum at the equilibrium point, and so on. This is x dot t, which in this case is going to be minus omega 0 a sine of omega t plus phi. So this is how the motion is described. If instead of pushing it in at t equal to 0, from the same distance I pushed it out, the phase would be slightly different, and I leave that as an exercise for you. As a second example of simple harmonic motion, let me now take a disc and pivot it at a point here so that it can oscillate about that point like this. Let this be one of the diameters. So its diameter goes back and forth, and I want to know what the frequency of oscillation is. As we have already learnt in rigid body dynamics, that whenever the forces and masses are distributed, we use the angular momentum. So in this case also, since the disc has distributed mass, the forces at each point, we use angular momentum concept, and therefore the dynamics is described as L dl dt is equal to the torque. In this case, the torque is going to be due to its weight mg, which will be at a distance if the radius is r sine theta if this angle is theta. And this is going to be opposite to the displacement, and therefore I can write I theta double dot is equal to minus mg r sine theta. That is the equation of motion governing the motion of this disc when displaced from its equilibrium position. Now I about the pivot is going to be I about cm plus mr square, and which is going to be equal to 3 by 2 m r square. Therefore the equation of motion is going to be 3 over 2 mr square theta double dot is equal to minus mg r sine theta. M cancels, one of the r cancels, and therefore the equation of motion that I have is theta double dot is equal to 2g upon 3r sine of theta. We are considering this disc which has been displaced from its equilibrium position like this. For theta less than 1, so that I can approximate sine theta roughly as theta, the equation of motion becomes theta double dot equals, there is a minus sign here, minus 2g over 3r theta, or theta double dot plus 2g over 3r theta is equal to 0. This is in the same form as the simple harmonic motion equation, and therefore theta is going to oscillate like theta is equal to some amplitude theta 0 cosine of omega 0 t plus phi, where phi and theta 0 depend on the initial conditions, where omega 0 is going to be square root of 2g over 3r. So this is another example that tells you how we see simple harmonic motion in everyday life. As a third example of showing that around an equilibrium point the motion is really simple harmonic, I take two charges of 10 microcoulomb each, separated by a distance of 1 meter, and I take a third charge of 5 microcoulomb put right in the middle. Right in the middle, electric field is 0, and therefore it's an equilibrium point. I want you to show, number 1, for motion along the line joining the charges, the 5 microcoulomb charge is at minimum u x. So what I am asking you to do is take these two charges 10 microcoulombs each, put a 5 microcoulomb charge in the middle, keep them fixed, these are fixed, and consider the motion of this 5 microcoulomb charge about this equilibrium point. I want you to show as I move about this, the energy goes up, potential energy goes up, as long as I confine the motion along this line. Number 2, calculate the spring constant K, which we have already decided is d2u over dx square at the equilibrium point, and therefore C, calculate the oscillation frequency omega naught for 5 microcoulomb charge if displaced from its equilibrium point along, let's call this the x-axis, the x-axis. What you can also do is calculate this potential exactly. It may look something like this, and see how the approximate potential that you are writing as 1/2 kx square looks like in comparison to the real potential. Also, up to what range of x is this approximation good, and up to what range you can describe the motion about the equilibrium point as the simple harmonic motion. As a fourth example, I would like you to consider a potential of the form A over x square plus bx square and calculate equilibrium point for a mass m, and B, calculate the frequency of oscillation when you displace this mass from the equilibrium point. You can of course go ahead and see how good the approximation 1/2 kx square is in approximating this potential, and for what range of displacement is this approximation good. So these are the exercises I would like you to do before we proceed.